fishing fleets head out for the Grand Banks, it's a nip and tuck race all the way. Every crew wants to be first on the fishing grounds, and the skippers will crowd on every inch of sail that the masts can carry, driving their boats to the limit. The Gloucester schooners are tough and seaworthy, and fast, even when their holds are filled with a record catch. They are working boats, these Gloucestermen, but even so, they've made their contribution to the history of speed on the water. And the principles worked out in generations of building Gloucester schooners have aided in the design of modern racing yachts. Of course, there have been many changes in building yachts for speed alone. Ranger, winner of the most famous of all yachting classics, the America's Cup race, exemplifies modern racing design at its best. She has a snubby bow, is full-bodied up forward, and has a low, gracefully extended stern. Her rigging has been scientifically improved, the working efficiency of the sails greatly increased through the application of the most advanced aerodynamic principles. And each increase in the power of the sails has thrown more of a strain on the mast. Surprisingly, Ranger's mast is hollow. It is built of thin sheets of light metal and is many times stronger than a solid mast of the same weight, better able to withstand the force of the wind driving into that huge area of canvas. This terrific side force, which may amount to as much as 50 tons, acts like a giant hand trying to bend the mast sidewise. We can see, by tightening the cables which help brace the mast, how this side force is counteracted. These cables, or stays as they are called, are fastened solidly to the deck and to the top of the mast. Now, if we put a model of a mast on a scale platform and attach the stays to a solid support, just as they were on the deck, we can see how the stays turn the side pressure on the mast into a downward force. Modern trains have been designed for maximum safety, even though weight has been reduced and speed increased. Railroad trains must stand a moving load. A sudden jarring impact is worse than ordinary compression loads. Here again, for greatest strength and safety, the engineers who designed the modern train use a box girder running the length of the car as a keel. The Oakland Bay Bridge, a triumph of modern engineering, is another type of structure in which the same sort of strain is met. The engineers who built it used a design that will stand up under tremendous loads, and they say will still be safe for service 1,000 years from now. Into the construction of this heroic monument to our times went a vast amount of materials and millions of man-hours. Moving across the largest stretch of water ever bridged is a constant stream of automobile traffic, and supporting this weight and that of the double-deck roadway are the mighty cables of steel wire exerting a powerful pull on each of the towers, which bear the entire weight. Now, here is an interesting point. In the morning, when the rays of the sun warm the cables and cause them to expand, the towers are pulled 6 inches toward the west. And when the afternoon sun shines from the west, the cables pull the towers 8 inches eastward. But of course, most of the cable's pull on one side is balanced by an equal pull from the other side. And as a result, both side pulls are turned into a downward push. If we could examine the huge girders that furnish the strength for the supporting towers, we'd find that they are hollow. And when automobile engineers needed the strongest design for a frame, it's not surprising that they too selected the same type girder that has proved its strength in trains, bridges, and yachts. Now suppose we try some simple experiments. Let's see how the box-type girder stands up under a sudden compression load, and compare it with the old-style open-face girder, shaped like a three-sided trough or channel. First, we'll put the old-style three-sided girder in our test stand. We'll use a fairly heavy weight and mark the spot where it starts its fall. Under a sharp falling load, the girder buckles. We can see in slow motion that it loses its hollow shape, flattens out, and no longer has strength to resist the bending. Now we'll test a hollow box with exactly the same amount of metal in it, and we'll raise the weight to the same place. If we raise the weight even higher, the four-sided girder can still take it. With the closed type four-sided girder, each side helps to keep the other sides firm and rigid so that it doesn't flatten out with the load. Using these dependable box girders, engineers have given us the modern motor car frame. Construction is simple and rigid. A strong backbone of steel. It is proof against all the shocks and strains of ordinary driving and a powerful safety factor in an emergency. The same sturdy type of girder is used in the braces as in the side members. Complicated bracing is not necessary. A frame that under any form of road punishment unfailingly holds the automobile's body and wheels in true alignment. Suppose we see for ourselves just how severe a shock the modern frame can stand. We'll move into the heavyweight division and see whether our frame can hold its own against far stiffer competition than it's ordinarily called upon to meet. And for this test, we'll use specially constructed bumpers on the front and rear, fastening directly to the frame, firm and rigid as the frame itself. The box girder frame, sound in theory and proved in practice.